Start.
Today we'll be looking into a topic of backpropagation through time, understanding time series gradient descent. And it is presented by myself, Atharva Gondai, Soham Phadke, and Spandan Chauhan. Let's start by the introduction to BPTT. What is backpropagation? Backpropagation is a fundamental algorithm used to train neural networks by adjusting weights to minimize error. It works by propagating the error from the output layer back to the input layer using the chain rule of differentiation. This allows the network to learn by updating its weights in the direction that reduces the overall loss. Why does it fail for sequential data? However, traditional backpropagation struggles with sequential data because of two major issues: vanishing gradients and exploding gradients. In long sequences, gradients can become too small, making it difficult for earlier layers to learn, or they can become too large, causing unstable weight updates. This prevents the network from effectively capturing long-term dependencies in time-dependent tasks. Introducing BPTT for time-dependent tasks. To address this, we use backpropagation through time, a variant of backpropagation specifically designed for recurrent neural networks. BPTT extends backpropagation by considering how past inputs influence future inputs. Instead of treating each time step independently, it unfolds the recurrent network across multiple time steps and applies backpropagation to its expanded structure. Now let's look at the mathematical formula of BPTT. First, we unroll the net, recurrent network, treating it as a deep feed-forward network, which can where each layer represents a different time steps. The same set of weights are used across all steps, ensuring that past information influences future predictions. Next, we compute the loss over multiple time steps. Instead of calculating the loss for a single output, PPDT sums up the losses from all time steps. Mathematically, this can be represented as where LT is the loss at each time step and T is the total sequence length. Finally, we compute gradients and update weights using the chain rule. PPTT propagates errors backwards through time, accumulating gradients from each step. Weights are then updated using gradient descent, where nu is the learning rate. Since gradients are passed through multiple time steps, this process can lead to vanishing or exploding gradients, making optimization challenging. Now let's compare BPDT with traditional backpropagation. While standard backpropagation updates weights layer by layer in a feed-forward network, BPDT updates weights by considering dependencies across time. Unlike traditional backpropagation, BPDT requires weight sharing across time steps and has higher computational costs due to longer sequence length. However, it remains essential for training recurrent networks as it allows them to learn from past information.
Okay, so this is Soham, and now I will be speaking about the key challenges in BPTT. So first of all, we have vanishing and exploding gradients. So the problem is that during BPTT, gradients are propagated backward through the time steps. For long sequences, repeated multiplication of gradients can cause them to either shrink exponentially, which is the vanishing problem, or grow uncontrollably large, which is the exploding problem. This makes it difficult for the network to learn the long-term dependencies effectively. What are the impacts? So the vanishing gradient hinders the weight updates for earlier time steps, causing the network to focus only on the recent outputs, while exploding gradients lead to instability in training, with weights diverging instead of converging. Solution techniques like gradient clipping and specialized architectures like LSTMs and GRUs are commonly used. Now let's talk about the computational complexity. BPTT requires unrolling the recurrent neural network over all the time steps, which involve calculating the gradients for each step. For long sequences, this results in high computational cost. Impact, it will slow the training and cause it to be resource intensive. What is the solution? We can use truncated BPTT, which we will talk about in the later part. Next, we have long-term dependencies. RNNs struggle to capture the dependencies across distant time steps due to the aforementioned vanishing gradient issue. As a result, the network fails to learn patterns that span long intervals. Impact, tasks requiring memory of distant events often suffer from poor performance. Solution, we can use advanced architectures like LSTMs, GRUs, and attention mechanisms to address this issue. Next, memory requirement. Problem, the BPTT requires storing intermediate states and activations for all time steps during the forward propagation. During to compute gradients during backward propagation. For long sequences, this leads to significant memory consumption. Impact, memory constraints can limit the sequence length, can be processed or require compromises like reducing batch sizes. Solution, memory efficient approaches such as dynamic programming based caching or recomputation strategies have been proposed. Now we'll talk about techniques to overcome challenges. The first technique is gradient clipping. What gradient clipping does is that it will limit the magnitude of gradients during back propagation to prevent them from growing uncontrollably. There are two common approaches. One is norm clipping, scales the gradients to a maximum of L2 norm if they exceed a threshold. And second is value clipping. It will cap the individual gradient component to a fixed range. For example, minus C to C given C is an interval. Impact, stabilizes training by prevent overshooting in parameter updates, and it will help convergence in deep networks like LSTMs and RNNs. Second, LSTM and GRU, which will help mitigate the vanishing gradients. LSTMs use input, forget, and output gates to regulate information via the cell states, enabling long-term memory retention. Whereas GRU simplifies the LSTM with reset and update gates, merging cells and hidden states for faster training. Impact, these gates will allow selective retention or forgetting of information, bypassing the vanishing gradient problem during BPTT. And last, we have the truncated BPTT, which will reduce the computational cost. It will split the long sequences into shorter subsequences to limit the gradient propagation steps. What is the impact? It reduces the memory usage by 60% and training time by 40% compared to the full BPTT. And we have the efficiency improvements. So the modern deep learning leverages parallelization techniques to overcome the computational bottlenecks. So first we have the model parallelization. It will split the neural network across devices, example GPUs, by distributing the layers or operations. Use case, we use this for large models with billions of parameters that will exceed a single device memory limit. Next we have data parallelism. It will distribute the input batches across devices, synchronizing gradients via collective operations. Example, all reduce framework. Use case, it can be used for CNNs and RNNs with large datasets. Sequence parallelism splits long input sequences across devices and integrates result via ring-style communication. Advantages, enables training on sequences which are greater than 100k token length by distributing the chunks. Now Spandal will be taking over.
Now I'll be going over the real world applications of BPTT and also the future of BPTT and its alternatives. So, one of the biggest uses of BPTT was in machine translation, where it was used to enable sequence to sequence models which would learn complex relationships between languages. So, translation systems like the early versions of Google Translate used RNNs, which were trained using BPTTs. However, modern systems have largely shifted to transformer architectures. It was also used in text generation systems like code generation through GitHub Copilot. Uh, and in speech recognition, BPDT is crucial as it converts audio waveforms to text. This systems can also process audio features, mainly MEL spectrograms, sequentially and learn to align them with corresponding textual outputs. In financial systems, in algorithmic trading, BPDT helps models learn from historical price patterns, volume changes, and other market indicators to predict future movements. In risk assessment, financial risk models use BPDT to learn patterns in time series data that might indicate increased risks. So, credit scoring systems incorporate sequential transaction data, and in this system, BPTT is used. Hospital systems use RNNs trained with BPTT to monitor patients' vital signs and predict deterioration before it becomes critical. In bioinformatics, BPTT helps models learn patterns in DNA, RNA, and protein sequences. Gene expression analysis uses RNNs to understand how gene expressions change over time in response to stimuli or during development. Now, for the BPTT is also used in time series forecasting uh, in situations such as predicting the energy consumption patterns to enable smart grid management. It is also used to model weather patterns for agriculture planning and disaster preparedness. It is also used in robotic systems, which enables dynamic systems for autonomous vehicle navigation. And it is also used to train industrial robots to perform complex assembly tasks. Now, the future of BPTT and its alternatives. So, first, the two main traditional solutions are truncated BPTT and gradient clipping, which Soham has explained in detail. So, the gist of it is that truncated BPTT limits propagation to a fixed window of time steps rather than the entire sequence, and gradient clipping prevents exploding gradients by enforcing a maximum gradient norm during training. Now, to combat the issues faced by RNNs, advanced architectures such as LSTMs and GRUs have been introduced. LSTMs have introduced memory cells with three specialized gates: input, forget, and output, which control the information flow. So, this architecture creates constant error pathways that mitigate the issue of vanishing gradients and thus enable the learning of dependencies spanning thousands of time steps. In gated recurrent unit, it simplifies the LSTM design with just two gates, an update gate and then a reset gate. So it basically works like an LSTM with similar performance but has fewer parameters. And then the modern approaches are the attention mechanism, which creates direct connections between any two positions in a sequence through weighted sums of hidden states. So this is the uh, basic feature which has been used to make the transformer based architectures. And in neural ordinary differential equations, models hidden state evolution as a continuous time process using differential equations rather than discrete steps. So this approach replaces traditional unrolling with numerical integration methods. And then finally, the hybrid approaches, which are quasi recurrent neural networks, which are basically a blend of convolutional networks with minimum recurrent pooling, which enable parallel computation across time steps during training, and transformer XL and compressive transformers, which are types of transformers which implement segment level recurrence mechanisms that reuse hidden states across segments without backpropagating through the entire history. And to finally conclude our presentation, in short, BPTT is a fundamental algorithm for training recurrent neural networks, enabling them to learn temporal dependencies in sequential data. While powerful, BPTT faces challenges like vanishing and exploding gradients, especially with long sequences, which has led to the development of more advanced architectures like LSTMs and GRUs. Therefore, however, understanding BPTT remains essential. Thank you.